So, I was just saying a bit in the previous session. Choose your A0 and A1 such that this is true. Just for convenience, such that your Legendre polynomial is PL of 1 when x is 1 equals 1. Okay. Now these polynomials, they are a weighted sum of powers of x, so x to power k, and then x to power k plus 2 plus 4, and so on. So these polynomials, they have a parity. You know, they're either an odd or an even function. And so you can form a formula for the parity. You know, parity just means, you know, either even or odd function. Remember, an even function, f of minus x equals f of x, and it has odd parity if f of minus x equals minus f of x. And it's a bit of revision, right? So here's a formula for the actual parity of these polynomials. It's minus 1 to power L. So if L is an odd integer, the parity of this polynomial, PL of x, will be minus 1. And that means it's an odd parity. And if L is an even integer, minus 1 to an even integer is plus 1, and therefore the parity of PL of x will be even. Okay? Now, knowing the parity of a function is very useful. You often save yourself half the work. You only need to just like solve half the equation, and then you know what the solution is to the other half of the equation by using parity, like a mirror image symmetry or a negative mirror image symmetry. So knowing the parity of functions can be very labor-saving. Right? Now the next bit of stuff is effectively just thrown at you. You're not as quantum mechanics, you are not expected to be real experts in DE's differential equations, but that specialty is so useful in quantum mechanics that you have to do some, right? Because the consequences of solving some of these differential equations are so enormous. For example, in the next few sessions, we will solve the associated Lagrangian equation, ALE, and get solutions that are of supreme importance to chemistry, quantum chemistry. We will show that probability distribution, for where the electron is around the nucleus, takes on these sort of weird lobe, sort of like wing sort of shape, like a dragonfly. Dragonfly wings are sort of like this. You'll see in a few sessions. So of great importance. So you need to know some of the details of this kind of differential equation, DE. So some of the results are just thrown at you. Now these polynomials they can be generated. So that there's a generator. That's some device, mathematical device, that cranks out the values of the Legendre polynomials, and it's this, like I say, just thrown at you. So it's 1 over 2 to the power L times, in the denominator, L factorial, and then the Lth differential of, with respect to x, x squared minus 1 to power L. Right? If you want, you could differentiate it once, twice, 3 times, and see if you get the same value. Well, of course you will, otherwise this wouldn't be put here. It's part of history, mathematical history. Of course you will. See if you get P0 of x is 1, and P1 of x is x, and P2 of x is a half into 3x squared minus 1, and P3 of x is a half into 5x cubed minus 3x, and so on. So you can generate your polynomials by using this generator, this expression. Now there's an alternative way of doing the same thing, except the variable is not x. You won't have x here. You've got cos theta, and this is an alternative way of generating these. So the weighted sum of these polynomials, but with cos theta as the variable inside, if you weight that weighted sum, converges to this. All right. Okay. Now new topic somewhat, a little. So now we move away from the Legendre polynomials and the Legendre equation, and now we talk about the slightly more complicated associated Legendre equation and associated Legendre polynomials. Okay. Now, associated Legendre polynomials, they have two parameters, not just L. The Legendre polynomials depend on just one parameter, L here. But the associated Legendre polynomials depend on two parameters, L, the same L, and also M. Okay, so this here is an associated Legendre polynomial because it depends on two parameters, L and M. And the way you can generate these associated Legendre polynomials by using the Legendre polynomials, so just P of L. Okay? So if you differentiate this with respect to x m times, the result that you'll get, well, if you multiply by this, will give you the associated Legendre polynomial according to this formula. And that, again, it's just thrown at you, right? If you really wanted to talk where all this comes from, and you could go on, a chapter or more. And this is just an appendix, right? And why is it an appendix? Because it's slightly at a tangent to the main discussion of AngularMmntm in chapter 7. So it's the sort of thing and level that you would put in an appendix, right? So, and